I have the pleasure to introduce to you Professor Jesse Thé, who is an expert in air pollution problems and also the president of Lakes Environmental, a company that specializes in giving user-friendly version of AirMod, CalPAF, and other software. So I'll let Jesse talk about artificial intelligence in atmospheric sciences. I'm closing my stop share. Very good.
So let me know when I can share. I can share now.
Yep.
All right, I'll share the full screen because if I have something else, I'll just do this. Can you see my presentation?
Yes.
All right. So hello, everybody. My name is Jesse, and I go by Jesse Thé because my Dutch name people can't pronounce anyway. So it goes, that's me. I am president of Lakes Environmental. Our dear friend Paolo already introduced. I'm also editor-in-chief of ENN.com. It's the largest environmental news in the internet. I teach at the University of Waterloo. I actually don't teach environmental science there. What I teach is artificial intelligence and quantum computing and AI and quantum computing. And I'm also the chairman of Toria, which is a quantum computing and quantum technologies company. So I'll be introducing you to, is my image covering the slide or not? You see just a slide? Okay. So when we are modeling atmospheric science, the computers need to discretize. We do not have, let me take a step back. To solve environmental problems, we have to solve massive amount of partial differential equations. These partial differential equations, they do not have a closed form solution like we have on the quadratic equation. Remember from high school. We apply the formula and then we get the two roots. Partial differential equations, then they do not have solutions. We need then to discretize them in space and time, such that we can then solve a series of approximations of the partial differential equations. Solving that in computers take an enormous amount of time. For the longest time, from the 1990s and the early 2000s, most of the supercomputers, they were used to solve partial differential equations, see computational fluid dynamics code and weather forecasting models, just as two examples. So then in atmospheric science, we have to analyze weather patterns, climate. Our solution here is pollution, and also other atmospheric processes such as photochemistry. Now, we still do that. We run at lakes, we have a supercomputer, and we run a WRF, a WRF, to generate weather and meteorological data for inputs to AirMod, CalPAF, and WRF-Chem. Now, why are we using artificial intelligence? It's not just us. There's a lot of people using artificial intelligence. Because we can approximate the solutions much, much faster than solving them using numerical models. Now, what is artificial intelligence? Well, there are various types of machine learning algorithms. And what is machine learning? Machine learning is a way that the computer learns by itself by looking at data. This is a simplification. So for example, more than 200 years, people use regression analysis. So regression analysis, let's say you have a straight line going through the points, you're learning with data. So you create that equation for the curve, or if you have nonlinear regression, then you get the equation for the curve that goes and represent the data. And thus, in the future, if I want to predict and I have the curve, I just apply the equation and get my solution. So this is the simplest machine learning example that you're going to get in your life, okay? So we learn with data. Machine learning, then, the modern one, is regression analysis on steroids. We used to use what I call the classical machine learning, which we would have things such as support vector machines and KNN, random forests, etc. But they are not as scalable as neural networks. Neural networks, we give the input, and then we show what the output should be. And inside, we have nodes. I'm simplifying here. It's this example right on this. Inside, we have nodes. So we need then to create weights on those connections between this node and this node, for example. We create and need to analyze the weights that when I do the input, it gives the right output. And it requires a lot of data to train this network, to refine it with the weights. Now, this thing is so incredible that it can then, first, it was detecting only if it is a cat or a dog, if it is a sheep. But then, as we grew in power with neural networks, new algorithms, and more computer processing power, we can start even creating videos out of this. ChatGPT is a neural network system. And then it associates words with your problem, and then it gets and builds very accurate solutions. So it is a large language model. ChatGPT is one of many. Okay, so this is artificial intelligence today, handles video, time series, it handles, and I have a large work on trying to apply AI to solve partial differential equations directly. So there is a theorem that says that a sufficiently large neural network, this is a theorem, it's a proven theorem, sufficiently large neural network can represent any function. I'm extrapolating and saying that a large enough neural network can represent an operator. And you say, what the heck is an operator? An operator, a mathematical operator, is something like an integration or a derivation. I get a function, integrates, get another function. So then I'm conducting research to solve partial differential equations, not the way we're solving today by using computational fluid dynamics, that's where I got my PhD in, but by solving them using neural nets. Now, AI atmospheric science works well even when you're not solving directly the partial differential equations, because it trains on a very large amount of data. And then I can use that to forecast hurricane trajectories. It has been used for that. It can use lots of data. People in the past, you hear these terms like big data. So it's complex and so on. Once it takes an enormous amount of time to train. And if the network is large, it will require thousands upon thousands of computers. As a matter of fact, Elon Musk just created one using very potent GPU, graphical processing units, each one having more than 10,000 processors, and it has 100,000 of those. So you are talking about over 10 million processors to train a system like ChatGPT. In the case of Elon Musk is Grok. Grok is just like ChatGPT. But you can train them to drive vehicles, you can train them to predict weather. And it's doing a fairly good job. It has immense advantages over the way we do things today because it is very efficient. Once you train, I can get my phone, my cell phone, and run an AI model because training requires a lot. Forecasting is just running multiplications inside the phone. And today, even a not very powerful smartphone can run billions of floating point operations per second. So you can do AI on your phone, okay? So it's very efficient to use to predict. And then the accuracy is increasing. So we have uses. Many different types of use. I can name them, but I will focus now because of our restricted time. I will focus only on atmospheric science. So for real time, for time series, which is very important, it is ideal to use neural networks. So I already discussed the machine learning. Machine learning is a much larger than just deep neural networks. And then deep neural network is the most accurate type of machine learning, okay? So natural language processing is ChatGPT or any other LLM. So there is not just ChatGPT, there is Llama, there is Mistral, there is Claude, and there is Grok from Elon Musk. So this, so you know, it applies and the results are just mind-boggling. In weather prediction, we do data analysis, so we can analyze data and we can recognize problems. We can recognize problems with the data, and we can also recognize if there is forecast things. If there is a tornado, a hurricane, we can get pollution problems, exceedances, and all that can be analyzed and forecasted, okay? And I have examples that I'm going to give, my own examples. I'm going to I'm going to show that I published papers on this already. Now, I teach at the PhD level remote sensing using AI. So I can use AI and then determine without having to have monitors everywhere. Because remember, monitors are a point in space, just a point. It doesn't tell you anything else. If I get satellite data, especially if I'm using multispectral satellite data, I can even analyze the composition of the pollutants, who is emitting, where it's going, using satellite and artificial intelligence. Air quality monitoring forecasts you can get. I will show examples in California where a photochemical model was not running well. And I know why it was not running well. And people in California then asked me to run using AI, and I'll show you that we predict much better than photochemical models for this case. I will explain when I get to the case why the photochemical model was not running well and my AI was. We also run photochemical models. I'm not against photochemical models. I'm telling you that there is a place for AI. Climate change research, we run scenarios for the whole globe in no time. The leading group to do this, we don't do this ourselves at Lakes. IBM and Microsoft have very large models to analyze climate change. It's not what we are doing. We are not competing with that because the data requires massive amount of computers. on the millions of dollars to do these runs, and we do not have the capacity. Now, from satellites using AI, we can do image segmentation, identify who is emitting. I can remove clouds. I can run and identify locations using AI. And I just using satellite and image segmentation, running my AI, I can also do weather forecasting, fire propagation on forest, etc. So these predicting extreme events, it's very good. Some of the numerical models, they fail when there are bursts, let's say wind bursts that can rip roofs off. The models that we use, let's say WRF, it's an average over the cell. And then they have the bursts are not smoothed out over the large cells. So running cells of 3 kilometers by 3 kilometers, and those bursts are not identified, and AI can identify it. And we can predict some, let's say, hail and other phenomena. So real-time weather forecasting for pollution, for tornadoes, etc., can be using AI. And the neural networks are very similar to the ones we use in ChatGPT, for example. We will just jump this a little bit because atmospheric chemistry is what matters. One of the tough ones to predict is ozone when we use photochemical models. And they are justified because they are secondary formation, and they depend on a lot of other inputs. And how we can do this, I will jump the AI. I'll have this available for you guys. Now, data assimilation is something that we do in large models like WRF itself. We do data assimilation. We get ground measurements, we get satellite data, we put it such that as we are forecasting, we get updated data from monitors and from remote sensing. And then we pass this to the AI. WRF does that as well, but then predicts not without AI. WRF-Chem as well, CMAC, ChemX, they all do that. Now let's see case studies, such that you see real situations. Hurricane prediction, I already discussed this, has been used and has been very accurate. Wildfire detection is one. Wildfire propagation is another one. Air quality monitoring and climate change. The climate change is not we have not run this ourselves. Everything else we have done at Lake. So this is the example I told you. This is in California. This Shafter, this is in a bit northeast of the greater LA metropolitan area. And the reason that the photochemical model was not predicting well there is because the model runs at a 3 by 3 kilometers. And everything that inside that 3 by 3 kilometer cell, it averages. Now, the valleys were like 1.5 kilometers wide. Now, when you have 1.5 kilometers wide valley and you put a 3 by 3 grid cell, it smooths out the valley, so you lose that information. So the model for that one, they should have run that at a 500 by 500 meter. But then it's a disaster because it is 36 times longer to run, okay? 36 times longer. So then I said I can solve that using AI. So what you see in the orange line is my forecast 24 hours ahead for ozone. And I use only monitor stations. And then using monitor station, the model learns how it behaves at the monitor station. And then knows that when the wind pattern is taking stuff inside the valley, it will bring back the stuff from the valley to the monitor station. So it learned by itself. And that's why I can do with this accuracy here. It's very accurate for our ozone prediction. Now, they said, well, we have another place in its Tranquility in Fresno, California, and it's not performing well, the photochemical model. I said, I will model there, and you'll see that it will work well. And you can see how well it is, 24 hours ahead. Yes, I'm predicting that it's higher than reality, but the trends, and look at these, most time I'm predicting right on, spot on, 24 hours ahead. And I use only AI on this. So now this is a different type of run for ozone as well, but I am running, not just using information from this station by itself. We develop internally at Lakes a graph neural network. And what is a graph neural network? This is ideal for a situation where I have many stations. I'll give you an example. If the wind is blowing from the northwest towards the center of Houston, it will go through this station, then this station, and then when it hits the center, then I have the measurements here. But look, if I have pollution here, and I have pollution here, and the wind is blowing this way, using my graph neural networks, I get, and I say, oops, large emission here. This pollution is gonna travel here and hit the sky in an hour or two, depending on the wind speed. And then I have the amount of pollution here with this one, it's gonna hit the center. So using various stations, and they are like a network that connects each other, and I have direction, not only the information that I get from the station by itself, but I see all the events that happen prior to hitting, this guy here contributing to this contributing to this, etc. And I can use that to train a more complex neural network and get very accurate results. And the results are this. The orange is my forecast. I hope you guys can see, I do not know. The orange is my, oh my gosh, they did it the other way here, my co-author. In this case, the orange is measured and the blue is forecast. You see here, these peaks, these are very difficult to obtain when you use AI by using a graph neural network. We also use something that is a little different than, and it would improve even ChatGPT, which in ChatGPT, the connections of the nodes, I use either sigmoid or ReLU, or I use Fourier transform solutions. And this increased the learning rate of the neural net. This is a more complex situation where I'm using it not just for atmospheric, but as you see here, I have a more complex situation, a more complex neural network. I do a neural network for the convolution, and this is for spatial information. And then I go and use we created this name, SAGE convolutional, because they use a graph neural network. So then in this river situation here for flooding, this is not for atmospheric science. If it is raining here, there is a flood propagation wave coming down here. The models get very complex. I do this also for ice, for floats of ice on the rivers, etc. Then I have contributions from everywhere prior to hitting my stations. And therefore, I get greater information than just measuring the station. So I use spatial using convolutional neural networks, a graph neural network. The SAGE here is our, let's say, new development, our invention. And we also use Fourier transform instead of just the simple sigmoid functions. And I get very good results. Since I'm a Dutch citizen and a Canadian citizen, I like to do things in Holland as well. And here, the forecast that people using previous work for forecasting wind speed in the Netherlands, they were always missing something. So what I did is I got all the stations throughout the country and also from the city where my family comes from here and from here. It's, you know, the cheese Gouda, it's not pronounced Gouda, it's pronounced Gouda. And so I have family from Gouda and from Den Bosch. And I put all these stations. And now if the wind is changing, let's say I get a northwest wind coming this way, and these stations here start perceiving, and then it learns that when that one increases, it learns by itself. And then this one will also increase. If the temperature here drops, this will also drop, and so on and so forth. So spatially using, and these are application directly. And you see here, and this is the Dutch wind speed paper that we published. You see this is no log. Like when you analyze air dispersion modeling, it is log base 10 here. And over at the bottom, this one, no, this one is linear. And you see how well we predict here on the, this is the prediction we make. And at the bottom is the measurements. So we measurement 24 hours ahead and look at how good we're getting this using only AI, no models. Again, I can use work and I can do data simulation work and can get good results. But I'm using only AI and we're getting pollution, we're getting wind speeds, we're getting cloud cover. It's good for forecasting for solar energy. And this is a case study. This is, I suspect maybe none of you have ever seen this. This is how we code in quantum computers. So I coded this in the IBM quantum computer and I ran it myself. So it's running a quantum computer and I'm using artificial intelligence in this quantum computer. And the quantum computer, if I use a neural net, that is the same architecture as a classical computer, the computer you have on your laptop, the same architecture, so we're comparing oranges to oranges. Then I get more accuracy in the quantum computer. So the quantum computer with the same architecture can learn more than the classical computer. Now the quantum computer is growing at 1 trillion times, 2 trillion times per year. Remember, the Moore's law is every other year, every 2 years, at double speed, and it's dead. Moore's law is dead. Now we have to multiply the number of boards to get, because it's not doubling every year anymore. But quantum computers is 2 trillion times year over year since 2020. As a matter of fact, it's a danger that next year or in 2026, adversary nations will break all the encryptions and banks will lose them. If they don't put quantum protection, banks will lose everything. Hospitals can be shut down, airports, the military, because we are in a society that all depends in classical computers. So we need to protect them with quantum proof encryption. And this other company that I showed to you, we develop quantum technologies, and one of them is get classical computers to be resistant to quantum attacks, okay? So let's just closing, and I'll do a review, and I'll stop here. Challenges and limitations. Data quality is a must. We need to prepare the data prior to training AI for atmospheric science. If we're training, we need a lot of compute and training. When I am predicting, I do not need large computers. I can use my smartphone, I can use my laptop. But when I'm training, I need some of these models, for example, ChatGPT runs cost when they finished all the runs they need. The cost of running, forget about the equipment, just the period that they ran and $100 million, okay? But to just do inference, to do prediction, then it's very cheap. That's why they can do free, offering to people free. Inference is very cheap, it's the training. So another problem with AI is it does not tell you why it got to the answer it got. I have solutions for that. I have presented. It is a problem of interpretability. It's just a name that people use in this field. They didn't invent this thing. So it got the result, but what affected the solution to get this result? You can't get that answer. We can't get that answer. It does not know why it got that answer. So what we do then is I run other models that give me answers and are interpretable, such that I know why a high ozone peak happened using a less accurate machine learning model. And then that's how I do interpretability. So I'm showing the challenge and the solution. And now to run and train the models requires specialized knowledge, but to train specialized knowledge, we all use here, I hope all of you have used ChatGPT, and ChatGPT anybody can use. So specialized skill to train, but to use, you do not need specialized training. Well, what is the conclusion here? It will enhance model accuracy, it's improving. If the type of work I'm doing, even if I'm not the one that's succeeding in solving partial differential equations, just an example here, guys. When I'm solving WRF or when I'm solving CMAC or WRF-Chem, a photochemical model, most of the time that the computer is working is inverting matrices. So if I have an AI that can invert matrices in no time, I can accelerate. I have a study, I'm doing this, I'm currently doing this. I get, and I'm running WRF. Why can't we use AI? I cannot use AI for any of the applications right now because we are in a regulated field. So AirMod is mandated by a lot of jurisdictions, not just in the United States, throughout the world. CalPAF is mandated in a lot of jurisdictions throughout the world. So I must use that model for that specific application. I cannot use AI. So WRF, for example, or CMAC. So what I have is a do iteration. So WRF will do, just a round number here, 100 iterations per hour to converge to a solution. So what I'm running is, I get, and I need to forecast what is the next hour. I forecast that using AI, provide my wind field to WRF, and then instead of doing 100 iterations, WRF will do 5. So it's an accelerator for WRF. And WRF is a regulatory model in a lot of places, and WRF-Chem and CMAC. So I can accelerate those models using AI, even though AI is not an accepted regulatory model, but accelerating those models still is an accepted model, okay? So now, one of the things that AI can be used in the future is you can do a weather forecast using your phone. Use an AI and without even going to the cloud, okay? So this is the future. So I'll stop here and I'm open for questions. You can send also questions to info@weblakes.com. We now own CalPAF, the CalPAF IP, intellectual property, the copyright. We own the CalPAF copyright. So we put in the CalPAF and the files at calpaf.org. And a lot of information we have, we put in weblakes.com. All right, questions?